Talking about high performance computing molecular simulations using LAMMPS, which is software that is developed primarily at Sandia. Here are some acknowledgements. We have Christian Trott, who's here with us and is going to be giving the next talk, and Lars Winterfeld, who've both worked on the user CUDA package for LAMMPS. My colleagues at Sandia, Steve Plimpton and Aidan Thompson, and then Greg Scanlon and Mary Payne, who are also here, will be giving a talk later this afternoon. And then at Oak Ridge, Mike Brown, Scott Hampton, and Pratul Agarwal. So I'd like to acknowledge each of them. So I'd like to start off, I know that not everyone here is an expert in molecular dynamics simulation. Probably some of you are vaguely familiar with it. So I'll cover a few of the basics, talk about why I think LAMMPS is a great software package and encourage its use, why we think it's a good idea to run LAMMPS on GPUs, and what is our GPU LAMMPS project, the efforts that we've made to get LAMMPS running well on GPUs, and what LAMMPS can now do on GPUs. And so that's basically what I'll try to cover in the time that I've got here. Oh, and just so you know, I prefer interactive conversation like talks. I know it's less formal, but if you have questions or comments along the way and you'd like to raise your hand, I think that would be good. Okay, so just a little bit about classical molecular dynamics. Each of n particles is a point mass. It can be an atom, but it can be a larger grouping of particles, or a mesoscale particle as well. It can be a group of atoms, and they interact via an empirical force law. So the empirical force law describes how the particles interact as a function of distance, the separation distance between the particles. And it can be described as pairwise forces, as in the Lennard-Jones potential or in Coulombic interactions, or it can be many-body forces. So it's not just pairwise interactions, but it can be a group of atoms and how they interact as a collection. There can be molecular forces, and then there can be long-range forces due to Coulombic long-range electrostatic interactions. And those can be modeled with something like the Ewald sum. We integrate Newton's equations of motion forward through time, F equals ma. And we advance as far as possible in time. And that's really the biggest challenge in molecular simulation today is being able to push out to longer time scales. That's what we would really like to be able to do. And then we can get the properties that we care about. We can extract the information from the molecular simulation by doing some time averaging or doing multiple ensembles versus what you would do in Monte Carlo simulation in terms of sampling. So molecular dynamics time step, we typically would use the velocity Verlet time stepping formalism, where we update the velocities by half a time step, update the positions using that velocity, recompute the neighborhood list if necessary, compute the forces at the new positions, and then apply any constraints or boundary conditions. So we add those onto the force, update the velocity by the second half of the time step, and then output any diagnostics that we care about. And in a typical molecular dynamics simulation, about 80% of the work is consumed in computing the forces. Now that's just a really rough ballpark idea, but that gives you kind of the idea of where the costs, the computational costs are in molecular dynamics simulation. Another 15% perhaps consumed by the neighborhood lists, and the rest is maybe only 5% of the computation. So these are the issues that really impact computational cost in an MD simulation. First of all, the level of detail. So if you can get the answers you care about on a mesoscale or coarse grain level, you won't need to simulate at the atomistic level, and you can save a huge amount of computational cost by doing something like that. The cutoff that's required, if you make a judicious choice in your cutoff, you can also save a huge amount of computational cost. If you don't need long-range electrostatics, that's another savings. And then if you use neighbor lists is a way to reduce the computational cost. Another way is to use Newton's third law, so that each atom's force on its opposite pair atom is transferred to the other atom rather than computed. The time step size, on the atomistic scale, we're typically limited to femtosecond time scale. But if we do it at the mesoscale, maybe it's picosecond or even longer time scale or time step size than that. But there's ways around that time step size limitation by, for example, rigidifying atomistic bonds. And then, of course, parallelism is what we would like to exploit in order to get around some of the computational bottlenecks that we've got. So how do we parallelize molecular dynamics simulation? MD, as you think about it, you quickly realize that it's inherently parallel, and we can compute all of the forces on each of the atoms in the simulation. We can compute simultaneously, and the positions and velocities can be updated simultaneously as well. Therefore, most molecular dynamics codes today are parallel, and they typically use something like MPI and a distributed memory. That's the types of clusters that most of the codes have been built for. So the computation should scale according to n, the number of atoms, and ideally in parallel would be the number of atoms divided by the number of processors that you throw at it. And we could distribute the calculation by atoms, by forces, or spatially, and the communication will scale accordingly. So there's different ways that we can break up the work, and we may even be able to exploit more than one method of parallelism to get additional speed up in parallel. So first, let's talk a little bit about the cutoff in the force field. So as I said before, the forces would typically consume up to 80% of the computational cost, and short-range forces should scale according to order n, and we assume that the simulation domain is a roughly constant density, and but by changing the cutoff then, if we double the cutoff, it increases the work by a factor of 8. So we really do want to be judicious about the choice of our cutoff, and we want to use it as short as possible. For example, if we're simulating Leonard-Jones particles, typically we'd simulate a 2.5 sigma cutoff. Whereas if we're doing all atom simulations, maybe a 10 angstrom cutoff would be more typical. Bead spring, just a very simple, more coarse-grained representation. We could just simulate the repulsive core of the particles and gain a huge speed up simply by truncating the interactions at a much shorter distance. And then after we determine the cutoff that we think we should use, we should check that assumption and try it at various cutoffs and see if it changes our results very much. It shouldn't. So another way that we can reduce computational cost, of course, is to do neighbor lists. And the question then is, how do we efficiently find the neighbors that are within each atom's cutoff? A simple solution would be just to test each atom against every other atom in the simulation domain, but that's kind of a naive assumption. And that would scale according to order n squared, which is really bad, especially as n grows large. So another idea would be to do what we call Verlet lists, and that way you just keep track of the atoms within a given range, plus a little bit of an extra, what I'll call a skin, outside that range, and you build that Verlet list once every few time steps, say once every 20 time steps. And then you only have to scan through just those atoms in that neighbor list. But you do have to make sure that none of the atoms move more than half of that skin distance before you rebuild the neighbor list. If that doesn't happen, then you could miss some interactions accidentally. Another idea would be just to divide your computational domain up into bins, three-dimensional grids. And then you only have to search the 27 bins within your cutoff radius, in the cube within your cutoff radius at every time step. And so which of those ideas would be better, a Verlet list or a linked cell? What do you think? Well, if you just think about a sphere inside versus a cube, obviously the sphere is going to be smaller because we're doing a spherical cutoff, and so a Verlet list is about 6 times faster, just looking at it that way. But really the fastest method is a combination of the two. You take a linked list, you start with the linked list, and then you build from that the Verlet lists. And you use the Verlet list on the non-build time steps. And this is a good method. It's order n in both the compute time and in the memory. It employs this constant density assumption, and that's what we implement in LAMMPS. So next, I'm going to try to sell a little bit here, sell you on the idea of using LAMMPS. I don't know how many actual practitioners of molecular simulation we have here, but it's also a good piece of software from a high-performance computing test bed perspective. So if you wanted to test a new idea on a new architecture with a new software, LAMMPS could be a good candidate for you to use. So just a little bit about LAMMPS. It's, as I've already mentioned, a classical molecular dynamics code. It's open source. It's freely available for download. So I don't know if this laser work. There we go. So anyone can download it at this URL. So if you're interested in actually playing with the software, please feel free to download LAMMPS and try installing it and running it. We think it's well documented. You may choose to disagree with that if you actually look at the documentation, but it does have a large amount of documentation, and I think that it's easy to access. One of the probably best features about LAMMPS is it's easy to modify or extend with new features and functionality. So if it doesn't do something that you are interested in or would like to do, you can add your own code fairly easily and be able to have that feature. We have an active users email list. We've got hundreds of subscribers. The slide is a little bit old. We already had our users workshop back in August of 2011, which was quite successful. I think we had over 100 participants that came into Albuquerque for that workshop. We've had tens of thousands of downloads, and the code has actually grown from about 53,000 lines of code to about 175,000 lines of code over the past several years. Now, as I mentioned, there's different ways to parallelize a molecular dynamics simulation. What LAMMPS exploits primarily is what we call a spatial decomposition. And what I mean by that is it divides the simulation domain into subdomains and assigns each one of those subdomains to a processor. And so if you've got n processors available, then you would break your domain up into n pieces and assign each one of those subdomains to a given processor. It can do some of these other fancy things like energy minimization, radiation damage simulation. It can do atomistic mesoscale or coarse grain simulations. It has a wide variety of potentials. I'll talk some more about those. And it has a wide variety of boundary conditions and constraints that it can do. This picture is supposed to represent the spatial decomposition, so you can think of the big box as the simulation domain and each of these little squares as a subdomain owned by an individual processor. And so the green one is representative of one processor's subdomain, and a molecule can actually span several domains and be partially owned by several processors. So that gives you an idea of how LAMMPS handles that parallelism issue. So why use LAMMPS? Let me answer this in a few questions. First of all, parallel performance. And I think that this is the area that is perhaps most pertinent to this workshop. But LAMMPS performs very well in parallel. It's been designed from the ground up to be an MPI parallel code. And we try to extend that and add additional parallelism that I'll talk about a little later. But this is an example showing a real-world problem. This is a rhodopsin protein that I built. It's solvated in a lipid bilayer, and this biomolecular simulation can be run inside LAMMPS. It's been scaled to a 32,000 atom problem size, and then on the left you see a fixed size simulation, so those 32,000 atoms are run on one processor on up to 512 processors, and we track the parallel efficiency on various computational platforms. Or we can scale the problem size up, and basically we just replicate the same domain n times, with n being the number of processors here. And so we can run a much bigger simulation domain, and we see that the parallel performance is substantially better in the scaled size sense. So you can see here that the fixed size problem is much more difficult. And that's actually the problem that's more interesting to most scientists. We really care about simulating for longer in time more than we care about simulating a bigger and bigger system. Okay? Usually the system's sizes of interest would typically be in the tens of thousands of atoms range. Of course, it really depends. So it's nice to be able to simulate big as well and to be able to have good parallel efficiency for really, really big problems. But we really, really like to be able to get out to the much longer timescales. And as you can see, that this is a much harder problem. To be able to take a fixed size problem and throw more and more processors at it and get additional speed up. So here's a different problem. LAMMPS can simulate a large class of problems, many different classes of problems. And this problem is an embedded atom potential simulating a metal. In this case, I believe copper. And again, we do a fixed size and a scaled size problem, and again, 32,000 atoms. And you see the same issue where the fixed size problem is harder to parallelize. It's harder to get good parallel efficiency. But that LAMMPS does reasonably well out to hundreds or even thousands and tens of thousands of processors. So the next answer, why use LAMMPS, is the versatility. As I've already mentioned, LAMMPS can do a lot of things. I think of it a little bit like a Swiss Army knife. It does a lot of different types of molecular simulation, or not even molecular, it's on up to the coarse grain. So it can do solid mechanics, material science, chemistry, even simulating breaking of chemical bonds. It can do biophysics, which many other molecular dynamics packages can do. Many of our quote-unquote competitor codes can do biophysics, but most of the other competitor codes cannot do all of these as well. And one of the areas that's kind of a growth area for LAMMPS now is granular flow simulation. And so these is a type of simulation that would be of interest to, say, mechanical engineers or geomechanics people. And this is something that LAMMPS does well. Another answer to why use LAMMPS is its modularity. So it is built in such a way from a software engineering perspective that the pieces are modular. And you should be able to use any, what we call a compute, which is kind of evaluates a quantity of interest that the user may have. Any compute should work with any fix, which determines kind of the thermostating and the time stepping and that kind of thing. And it should work with any pair style, which is really the force fields. And that should work with any of the atom styles. So we should be able to mix and match any of these parts together. The user should be able to take any of these parts and use any of them together to create any kind of simulation that they want. So the answer number 4 to why use LAMMPS is that it's got great potential coverage. And I've already touched on this a little bit, but it's got lots of different pairwise potentials, such as Leonard-Jones and the Buckingham potential. Lots of different charged pairwise potentials. It does Coulombic interactions, point dipole interactions. It does many body potentials. These are primarily for metallic materials or semiconductors. And we'll talk more about some of these later. It can do reactive force field potentials, electronic force field potentials, coarse grain potentials, mesoscopic potentials, and it can even do, of course, long-range Coulombics using, as I mentioned, Ewald sum or something like the particle mesh method. And of course, it's got a wide variety of not just pairwise interactions, but the bonded potentials, the angular potentials, dihedrals, impropers. It can do several different kinds of water potentials, just different water models, implicit solvent methods, and it's got force field compatibility with some of the biomolecular simulation packages as well. So you can do straight comparisons there. So the range of potentials, really we range from biomolecular materials to polymerics to material science type problems, mesoscopic, and one of the really nice features is that you can use hybrid combinations of these too. So say for example you wanted to do a simulation of water on a metal, and you had a good water force field and a good metal force field, but you wanted to be able to use those together. Well, LAMMPS provides the tools to be able to do some of those kind of hybrid type problems that you might be interested in. So probably the best feature, as I mentioned before, about LAMMPS is that it's easily extensible. And if you've played with other software packages that you picked up in the past and tried to extend them for your own purposes, you can feel the pain of that type of problem. Well, LAMMPS really tries hard to get away from this by its nice modularity, and it's got these various styles, and you can add one of these new styles to your own liking and without affecting the rest of the code. And in fact, about 80% of LAMMPS is extensions that people have written, us or other people have written. So really only a small fraction of the total number of lines of code is core LAMMPS. The rest is extensions that people have added subsequently. And this is enabled by the nice software engineering and the C++ that LAMMPS has written in. So next up, maybe perhaps more pertinent to this audience, is why run LAMMPS on GPUs. We've chosen to do this And why have we gone down this path, and what do we hope to gain from that? Well, first of all, we try to listen to our users, and our users have been pounding on us on this for years and saying, well, why can't we run LAMMPS on GPUs yet? So we listened to that, and we tried to add some GPU capabilities to LAMMPS. Another argument is that the future is many-core, and that GPU computing is leading the way. And I think that that's probably not controversial. The next few statements that I'll make here, some of you may choose to argue with, and that's fine. But let me make these statements anyway. So I'll say that GPUs and NVIDIA's CUDA are industry leaders in computing on GPUs. And they've all already shown impressive performance, and that each generation is getting better. As you probably are aware, on GPUs you can get more flops per watt, and then I'll make this kind of controversial statement that CUDA is way ahead of the competition. And so feel free to argue with me about that offline or here. But that's my perception, and the landscape is changing very quickly, and that may change soon. So another motivation for running LAMMPS on GPUs is that other MD codes are doing this too. So it's a little bit monkey see, monkey do. We see other MD codes doing this, and we figure we should jump into this as well. And they've been able to show very impressive speed ups. Some of the other codes that I mentioned here, and there are many others that are trying to do molecular dynamics on GPUs, and most of them have shown very impressive speed ups. So another reason, of course, as I've already mentioned, is access to the longer timescales. So if you think about timescales on, say, a log plot, for example, just in the field of protein dynamics, many of the events that we care about, even things like secondary structure rearrangements, are going to occur on the microsecond timescale. We'd love to be able to get to even longer timescales, and to be able to compare with our experimental colleagues directly. We would like to, again, get out to the much longer timescales. But if you look at molecular dynamics, in the 2005 timeframe, we were only really constrained to the nanosecond timescale. Now it's more like the microsecond timescale with really modern hardware and a heroic simulation. You can get out to that kind of timescale. But still, there's lots of events that we would love to be able to access, and in the future we will likely be able to access more. So if we look at a plot of historical top 500 computers and project into the future where that's going to be, we estimate roughly 2018 we should see an exaflop computer, and I think that probably few of you would argue with that. And so we want to be prepared for that exaflop computer, because they'll likely have GPUs or something similar on them, and we need to be ready for that. So another plot here just to show that the growing concurrency. So supercomputers of the future will have a much higher concurrency, similar to what GPUs have. So the fundamental assumptions of the system software architecture of the past may not apply in the future, because this rapid exponential growth in parallelism was not really anticipated. So another reason to run LAMMPS on GPUs is that future architectures are very likely to have GPU-like accelerators. We expect the high concurrency, we expect them to be very different from current architectures, and we expect increased floating point capacity from typically it will be from accelerators if it's anything like what we see today. GPUs, FPGAs, or cells are probably something different, or probably some combination of a CPU and a GPU into the future. And as you know, some of the significant challenges that we're confronted with are concurrency, power, and resiliency. From a hardware perspective, those are some of the challenges that we face. So let me talk now a little bit about what I'd call our GPU LAMMPS project. This was the effort that we have undertaken to GPUize our LAMMPS software. So the goal was to get to better time to solution, which I think you clearly see the reasons why we care about that, on particle simulation problems that we care about. But in order to do this, we want to harness the compute power of GPUs. And we would specifically like to keep all the cool features that we have in LAMMPS and be able to push those onto the GPU. we'd like to maintain all of LAMMPS' functionality while improving the performance. And we figure, based on other people's experience, that we ought to be able to see somewhere between 2 and 100-fold speed up on problems that we care about, but of course depending heavily on how we do that comparison. In particular, we would just really like to harness the next generation hardware, specifically CPU, GPU clusters. So our strategy is not aiming to push the entire LAMMPS code onto a single GPU, but we're really targeting clusters, CPU, GPU clusters. And we would like to do this by doing what I'll call a dual parallelism. Spatial decomposition, like LAMMPS has always done, with MPI between the CPU cores, but then do another layer of parallelism, of force decomposition, with CUDA on the individual GPUs. And of course, we like to leverage the work of internal and external developers, which we've done. So what can LAMMPS now do on GPUs? We've got actually 2 independently developed packages available now with LAMMPS, and the next talk will go into more detail about this, but just to segue into that, the GPU package was primarily developed by Mike Brown at Oak Ridge, and then the user CUDA package was developed by Christian Trott in Germany, and he will be the next speaker, and he'll go into more detail. But just very high level, I want to give a comparison between these 2 packages that LAMMPS has. And when I say package, I mean it's an extension to the LAMMPS code that enables you to run on GPUs, to do use LAMMPS but do it on GPUs. So the GPU package, it was designed to exploit hardware configurations where you've got 1 or more GPUs coupled with many cores or multi-core CPUs. And so the design intent there was to be able to harness the entire node of available CPU and GPU resources. And one of the biggest disadvantages of this approach was that it moves the atom-based data, the coordinates, the forces back and forth between the CPU and the GPU every time step. And if you know about how these architectures are in the communication between the CPU and GPU, you know that that's somewhat of a bottleneck. So that's the biggest downside that I see with the GPU package. The neighbor list can be constructed on the CPU or on the GPU, and you can do asynchronous force calculations simultaneously on the CPU and GPU. So you can use all of the available compute resources on the node simultaneously. And it has OpenCL support, so it's not only limited to NVIDIA hardware, but it can also run on other multi-core hardware, AMD, Intel, other into the future. Now, the user CUDA package is designed to allow the simulation to run entirely on the GPU, except for, of course, it needs to use the CPU for interprocessor MPI communication, so that the atom-based data doesn't have to move back and forth between the CPU and the GPU on every time step. So this is a big advantage with the user CUDA package. So the speed up advantage with the user CUDA package is even better when the number of atoms per GPU is large. So this package works better if you've got a huge amount of, a very large number of atoms per node. The data stays on the GPU until a time step or where there's a part that's not been GPUized is invoked by the user. So this is, again, the big advantage of just leaving the data on the GPU. And of course, the neighbor lists are constructed on the GPU. But a big downside from my perspective of the user CUDA package as compared to the GPU package is that you can only use 1 CPU core with each GPU. And Christian may choose to talk more about this, but this is perceived as a limitation, especially when you've got a multi-core CPU sitting there available and only 1 GPU. So it doesn't necessarily exploit all of the compute resources you've got on a given compute node. So in terms of force field coverage between those 2 packages, you can see in red, I've marked the GPUized portions of LAMMPS in terms of force fields. And so a large number of the simulation cases that our users care about can now be run on the GPU. One example of a quite expensive computation is aspherical particle simulation, and these could be used for, say, liquid crystal simulations. It's very expensive to do aspherical particles in molecular dynamics, and they're roughly 30 times more expensive than Leonard-Jonesian. And you can see that depending on how you measure it, if you measure just versus one CPU core, you can get on up to 360-fold speed up. So that's kind of the upper bound of what kind of speed up we would expect, and it depends on how we're doing that comparison. And here it's not an entirely fair comparison because we're using 4 GPUs and we're comparing against just a single core of a fairly slow CPU. Now, if we do a more fair comparison and look at the entire CPU node, the speed up is much less impressive. It's 120x instead of 300 and some x. But still, nonetheless, a very impressive speed up. And admittedly, we've handpicked a rather expensive potential. And so this is kind of still a best case scenario in terms of what we can expect in GPU speedups. But if we look at a fair comparison and do across a wider range of the simulation capabilities that LAMMPS features, and we look at double, mixed, or single precision, we see that the speedups are much more modest when we compare versus a quad core and we just use one GPU. And so this is what I would consider a more fair comparison. And using force fields that are much less expensive, like granular here, the speedups are not nearly as impressive as you would get if you did a very expensive calculation, a very expensive force field. So some of the lessons we've learned, it's not easy to port a legacy code to run efficiently on GPUs. This has been a lot of work, and some of you may say, well, no duh, that we would have anticipated that, but I think some people have the misinformation or the false idea that you could easily port legacy codes to take advantage of GPUs, and I think that that's not the case. GPU memory management is tricky. The host device communication is a bottleneck. As we've seen, if we move more of the calculation to the GPU, we improve the performance, but it requires more code verification, conversion, and maintenance. So the optimal algorithm on the CPU is also not necessarily the optimal algorithm on the GPU or on a hybrid cluster. So you may even need to change the underlying algorithm, not just the way that it's coded up. And that's a real challenge. Mixed or single precision is okay in some cases, I would argue, and it's considerably faster, but it's preferable to give the users the choice whether to use single precision or double precision or mixed precision. And optimal performance requires simultaneous use of all available compute resources. And so ideally, the ideal software will take advantage of all the CPU and GPU or whatever compute resources are available on a given node. Remaining challenges, corresponding limitations, merging disparate visions of where we're going from here, better coverage of LAMMPS' capabilities we would still like to get. Of course, better performance is always desirable. Quality control, we kind of rely on users sometimes to report bugs, and that's not necessarily the best quality control method. And then just code maintenance, syncing the GPU portions or the GPU modules within LAMMPS with the rest of LAMMPS, supporting users and doing the bug fixes. And so it's really lots of challenges ahead for this effort on porting LAMMPS to run on GPUs. Future areas of development within LAMMPS, we'd like to, of course, continue to alleviate the timescale and spatial scale problems. We'd like to, one area that we're currently working on is improve force fields for better molecular physics. So better force fields are going to be more expensive, and thus we'll want to immediately port those onto the latest next generation supercomputing hardware. But that can give a much more accurate simulation, so that's desirable for our users. And then, of course, we'd like to add new features for the convenience of our users. I'd like to also note these last two things of some rapidly growing or some current growth areas for our LAMMPS development efforts. We're rapidly growing an open MP capability. So this is for efficient harnessing of multi-core CPUs. And if you're interested in this or would like to hear more about that, please come talk to me. And that's in addition to the GPU capabilities that we've discussed here. And then we're also working on a new long-range electrostatics simulation capability within LAMMPS based on the multi-summation method. And so that's an example of development of a new algorithm that's better suited for next-generation high-performance computing. So to get us away from doing 3D FFTs on a next-generation hardware cluster, we've changed our method for long-range electrostatics to a more efficient method that doesn't require the 3D FFTs. And with that, I'll thank you for your attention, and I'd be happy to answer any questions.